My goal is to convince you by the end of the talk that big data is low rank. So you'll see whether or not you believe me. Okay, so I can tell you where my interest in low rank data originated. This was this is an application sort of stylized from something that I saw when I was working on the Obama 2012 campaign. So there they had information about, right, so this is a US electoral politics, so they had information about every voter in the United States. So here I'm showing 4 rows, but imagine there are maybe hundreds of millions of rows. And so you've got information about every person who's registered to vote in the United States. So maybe you know something like their age, their gender, maybe what state they live in, their approximate income, their approximate level of education, and a bunch of other features you can buy. So people will sell you features like, does this person like Volvos, or do they like Mercedes, or do they like Volkswagen? They'll sell you all sorts of features. So you have a lot of stuff that you know or approximately know about these people. But of course, the more things you know about them, the more missing data there is. And the more things you know about them, the more the things that you know about them are kind of weird, right? Maybe not numerical features, but maybe something else. So here we've got age, which looks numerical, but of course it's also positive and integers. We've got gender, which in this data set is coded as binary. Maybe in other data sets it wouldn't be. We've got state, which takes on 1 of 50 values. Income, which once again, positive numbers, but maybe missing values are particularly likely to be maybe high, maybe you know, you don't really know. And education, which is ordinal. Okay, high school is less than college, is less than PhD. Okay, so we're in the context of this kind of data table, and when I was a data scientist working at the Obama campaign, my boss came to me and said, well, can you cluster these people so we understand who they are? And you look at this data and you're like, what do you mean by cluster? Right? Like, are people, for example, if I were going to cluster these like as Euclidean vectors, I'd have to decide something like, is the difference, suppose 2 people were exactly the same except they differed in their level of education, high school versus college. Now compare that to 2 people who are exactly the same except they differ by what state they live in. Okay, which ones are closer together, which ones are farther apart? It doesn't, it somehow semantically doesn't make sense. It seems like you have to decide things that you don't want to have to decide in advance. You want to be able to learn this from data. Okay, so how do we do these basic things? How do we detect demographic groups? How do we cluster, in other words, cluster? How do we find typical responses within those demographic groups? How would we identify related features? Maybe there's some features that we're buying we don't have to buy. And how would we impute missing entries, right? So if we don't know, say, the level of education of this 41-year-old from Nevada, can we predict what that would be? Okay. And all these things are hard because the data is very large, it has missing values, and the data is of a variety of different types. Okay, so it turns out this problem occurs in more places than just electoral politics. So I'll show you a bunch of examples throughout this talk. But you can imagine that the examples, I'm going to call the rows in this data table examples. They might be patients in a hospital, respondents on a survey. They could be assets in a financial model. And there are going to be a bunch of columns, which I'll call features. And these could be things like test responses, questions, answers, or maybe performance indicators for these financial assets. So the ith row will be the feature vector for the ith example. The jth column is the value of the jth feature across all the examples. Okay, so if we're going to do anything like imputation, we need to make some structural assumption. And the one that I'm going to make here is a low-rank assumption, and I'll try to validate why that's a good assumption, both via how well it works and also some theory. So here's the low-rank assumption. I'm going to assume that there is a number k that is much, much less than the number of rows and the number of columns in this data table. And I am going to look for a decomposition of A as the product of 2 matrices, one that's skinny, X, and one that's fat, Y. Okay, so what's maybe peculiar about this is that X and Y are both numeric, or real-valued matrices, and A is a data table. Okay, so I've got some explaining to do to say what does it mean to say that a numeric matrix is approximately equal to a data table. Okay, but once you figure out what that might mean, then you're in luck because this kind of model enables you to answer all the questions that I set up at the beginning. So you can think of X and Y as a compressed representation of the data table A. So that's advantageous for its own sake, maybe to denoise the original data. You can think of any row of this matrix X as being a compressed representation of the corresponding row of the data table. Okay, so that means I've got a low-dimensional, real-valued vector representation for every person in my data set, right, every row in my data set. And I also have, as the YJs are numeric, right, real-valued vector complete vector representations for the features. Okay, so those are both super, super useful, right? I could cluster them, I could plot them, I could do anything I want. And the last thing is that you can impute missing data, because the inner product, which I'm writing as xi times yj, so xi is a row vector here, xi times yj approximates the missing value aij. Okay, so that's fantastic. Now all we have to do is figure out what squiggly equals means. Okay, okay, so why would you do this? Just to summarize, right? To reduce storage, maybe to understand your data by visualizing or clustering it, to remove noise from your data, to impute missing data, and maybe just to simplify data processing by using these vector representations for your examples in place of the original messy data vectors. Okay. So how do you do this? Well, the simplest setting in which this is very easy, and everyone learned this in kindergarten, is principal components analysis. Okay, so what is principal components analysis? This says, okay, so suppose my data table is actually a matrix. It's completely observed. Okay, so I just have an m by n matrix, and I want to find a low-rank representation of it. One way of sort of making that a concrete optimization problem would be to say I'm going to minimize the difference between A and x times y in a sense of least squares error. Okay, so my variables are x and y, and they're low-rank, skinny and fat matrices respectively. So people have been doing this for over 100 years. And part of the reason why they've been doing it for so long is because this problem is really easy to solve. So I looked back at Hoteling's 1933 paper, and let me tell you how he solves this problem. It's amazing. So he has data from some educational survey, and so he has like 4 things that he knows for some large number of individuals, and he writes down the covariance matrix, a 4x4 matrix, in his paper. And then he says, here's a random length 4 vector. I'm going to multiply my matrix times this vector, and here's the output. You know, he writes down 4 numbers. And he says, now I'm going to multiply that matrix by that vector again. Now I'm going to do it again. Now I'm going to do it again. Oh, this output is not so different from what it was at the last time, so that's my answer. Okay, so he does power iteration by hand in the paper. I mean, this is what makes PCA you know, so popular for so long, is that it's really, really tractable. Okay, so more generally, right, you can get the solution to PCA via truncated SVD. So a top K SVD, and you can read off the X and Y directly from the truncated SVD. I guess it's worth mentioning that actually a lot of people, it's surprising to me how many people still think that computing the truncated SVD is like n cubed complexity. Okay, that's not true. It's something more like input sparsity plus the final size of the factorization. So the size of x and y together. And you can do this using randomized linear algebra methods. So both this is true in the matrix case, and it's also true in the tensor case, which is pretty cool. So there's a lot of work on this. I've worked on this with Joel Trop, Volkan Sever, Albertsever, but there's a large literature on this. So anyway, the SVD is easy. Good. And the sort of nonlinear dependence is on the rank parameter k. Okay. But in order to generalize, so that's true for real valued matrices. But if we want to generalize to these weird kinds of data, then I actually don't know any of these you know, really nice, really fast methods. And the best one that I can tell you about, and the one that we'll sort of generalize from this setting, is alternating minimization. Okay, so the way that works is the following. You fix a guess for y and minimize the subjective over x. That's a least squares problem, super easy, super fast. Also parallelizes over the rows of x. Okay, now fix that guess for x, minimize over y. Fix that guess for y, minimize over x, continue. There are stationary points of that are that iteration that are not the global minimum, But with probability 1 over random initializations of y, that does converge to the global minimum. Okay, so in practice, alternating minimization for PCA also succeeds. Okay, so how do we generalize to these other kinds of data? There are 3 changes that I'm going to make to my objective to make this generalization. So one is I'm going to replace the sum, my loss function, which before was quadratic loss. I'm going to replace it. Does this make a no? Okay, there's no laser. Okay, that's fine. I'm going to replace my quadratic loss with, oh, mouse. Yes, of course. Okay, here we go. I'm going to replace my quadratic loss by some other loss function that tells me how angry I am to have approximated x times y by this value a. Okay, so you're right. If a is something like college, it does not make sense to subtract college from 7, right? Or vice versa. So instead, I have some loss function that describes how annoyed I am to approximate college by the number 7. Make sense? Okay. Second change is I'm going to take the sum of the loss functions, not over every entry, but just the entries that I've seen, those in some index set omega. So that's pretty straightforward, right? I shouldn't be penalizing myself for things that I don't know about. And then the third change is maybe to add some regularization. And this can sort of stabilize my estimate. So probably if you don't know what else you're doing, then quadratic regularization is the way to go. And you can actually prove some very nice statistical properties of your solution if you use quadratic regularization here. For those of you sort of equivalent with the convex formulations of these things, that actually ends up being equivalent to regularizing the nuclear norm of x times y. Okay, so once I've done these changes, the objective can be NP hard to optimize exactly, but I can still run alternating minimization, and it still gets to something kind of interesting. Okay, so here's the algorithm that I would recommend in practice. I would fix a guess for y, minimize the objective over x in parallel. I would fix that guess for x, minimize over y, possibly in parallel. So these subproblems are easy to solve. They're all convex, as long as the loss and regularizers are convex. The objective decreases at every step, so it converges. It's not guaranteed to find the global solution, but in our experience, it usually finds a very good solution. So as long as your regularizer is quadratic, I don't know of bad examples. I know of bad examples when the regularizer is, say, L1. And it's naturally parallel, so it scales to very large problems. Okay, so what kind of losses should you pick? So here I would say, right, you would pick losses that are adapted to the kind of data. Okay, so if you have real value data and you think you have sort of Gaussian errors, and use a quadratic loss. If you think you have larger errors, then maybe you want to use a more robust loss like the L1 loss or the Huber loss. For Boolean data, maybe the hinge loss or logistic loss. But essentially at this point, you can just go through the machine learning literature. You can say, so suppose I wanted to solve an ordinal regression problem. What are good ordinal loss functions? I will plug that in here. Okay, so we're essentially sort of reducing this problem of missing value imputation or dimensionality reduction in these very large data sets to regression problems that are very well studied. Okay, and that's because we're here, the framework is saying, well, I don't know the covariates, right, but I'm going to learn the covariates. Those are the x's, right? And once I learn the covariates, then they're completely observed, they're real valued, and the problem reduces to more standard regression problems that are more studied. Right, this one versus all loss is equivalent to, the harder ones are ordinal and categorical data. Okay, so the one versus all loss that I've written down here, it's equivalent to it's equivalent to taking your categorical value and turning it into a one-hot vector, right? That has a 1, right, for the value observed, and 0 for all of the possible values that you did not observe. And then you can do either logistic regression or maybe an SVM or something for each of those values. Okay, so this one versus all loss is packaging that up into a single loss function. And you can do something similar for ordinal regression, which is what I'm calling the bigger versus smaller loss here. That doesn't seem to be as well known within the machine learning community, but there's actually a beautiful paper by Srebro and Rennie that was just a workshop paper from 2005, I think, that introduces this loss among others. But in my experience, it works extremely well, just as the one versus all loss works very well for categoricals. Okay, so that's all sort of practical stuff. Regularizers, you can choose in a bunch of ways, usually to impose structure. If you don't want to impose structure, then the quadratic regularizer is absolutely the best one to use. Okay. How do you impute missing data? It's actually really straightforward once you have this formulation. Okay, so if you're going to impute a level of education, you would better make sure that you don't say 7.2. You have to actually say a level of education. And the way you do this is via a loss function, which provides this canonical link between the numbers, right, this XY representation, and the values, this A representation. Okay, so if you fit your model, sort of X times Y, and you want to find the most likely value, what you do is you minimize the loss function over its second argument. Okay, and that returns to you just formally something that's in the right domain. Okay, so if your loss function, for example, is quadratic or L1 or Huber, it will just return to you X times Y, so it's what you expect. If your loss function is either logistic loss or hinge loss, actually in either of those cases, you can sort of check that when you minimize over A, you're going to get the sign of X times Y. So it'll be +1 if it's positive and -1 if it's negative, and that's exactly what you would expect. Okay. Great. Okay, so let's see how well this kind of thing works. And in particular, I guess it's relevant to compare it to PCA, which is people's sort of default option. They would say, how would I do this? I would take my data, right? And maybe it's ordinal, maybe it's categorical, maybe it's Boolean. I don't care. I'm going to encode it as real values, right? So I'll do the encoding sort of first, right? I'll take my ordinal levels. Maybe someone has told me they're paying on a level on a scale from 1 to 7. And instead, I'm going to encode those as actually the numbers 1 to 7 and run PCA on it. Okay, so I want to compare that with doing this more complicated procedure. Okay, so here's an example. This is synthetic data. But what I want you to imagine is that this comes from a hospital. Okay, so in this hospital, I have data from a bunch of different patients. These are the rows. And I have data from 3 different kinds of tests. One kind of test returns a real valued outputs. That's the first chunk of columns. The second chunk of columns returns Boolean outputs. And the third chunk of columns returns ordinal outputs, right? So like what's your pain on a scale from 1 to 7. Okay. But something terrible has happened to our hospital information system, and we've lost 2 of the kinds of data for half of the patients. Okay, so this is embarrassing, and rather than admit this to the patients and ask to collect the data again, instead we're just going to impute the missing data. Okay, so please don't try this if you're in charge of a hospital information system, but we'll see. Okay, so if I do this with PCA, so I'm just using the quadratic loss, right? But not the quadratic loss, but just summed over the missing values. So it's not quite PCA, but close. Then here's the imputations that I get, and here's the error. So it looks pretty good here. Green is 0 error. So like there's some yellow is unit error, and it makes sense that if you have error on Boolean or ordinal data, you have to have at least unit error. So interestingly, we never have actually more than unit error. So that's actually pretty good already. But if I do it with the loss functions that are adapted to the kind of data, so here I'm using a Huber for the real values, hinge loss for the ordinals, and here I'm using hinge loss for the Booleans and ordinal hinge loss for the ordinals, I can do better. Okay, so you can see the amount of green increased. Yes?
Are there errors on the bits where you have the right data?
Yeah, so this is kind of interesting, right? So you can think about this as a method for denoising or a method for imputing missing data, right? So if you're just imputing missing data, then you would get no error for anything that you had an observation on. But if you think about this as denoising, right, then you might actually want to have some error on the bits that you'd have observed, and maybe you actually believe that more than the original data. Okay, so it's kind of interesting to see what it is, even if in the context of your hospital information system, you would probably take the original measurements. Yeah, good. Okay, so we have implementations in a variety of languages to fit these models. So they exist in Python, Julia, in H2O, in Spark. So here's a Julia example, and you can see that we have some default. We must have default loss functions because you inform the low rank model. So this is forming it on a data table A with 5 columns, and it can sort of see the types of the columns and do the right thing. Choose the appropriate loss functions, even if they're not the best loss functions. Okay, and then fit it. Okay, so how do you validate a model like this? So how do you choose these model parameters? So that's actually one of the worst things about this. I mean, about sort of regularized approaches to estimation in general, right, is choosing model parameters. So here, you can just leave out 10% of the entries, use the model to predict them, see what model parameters predict those entries best. Okay, so here, for example, I tried a range of different rank models, so rank 1, 2, 3, 4, 5. The rank and then also as a function of the regularization parameter, which is on the x-axis here. So you can see the rank 1 model in blue does not fit very well. The rank 2 model fits a little bit better. Rank 3 through 5 all fit really perfectly well because the true data is all actually rank 3. But you can see when I have overestimated the rank, then I want a little bit of regularization. So the best lambda is around 2. Whereas when I've exactly estimated the rank, then 0 regularization is the answer. Okay, so somehow the reason for the regularization here seems to be to stabilize sort of the fact that I might not be able to estimate rank exactly. Okay, I want to show you sort of the power of this class of models, and then I want you to sort of ask why are these working well. Okay, so we actually did try this on a real hospitalization data set, and we saw the same kind of phenomenon. So here the rows were single hospitalizations, so we knew the demographics of the patients, the diagnoses that were made, procedures that were performed, and comorbidities, so other diseases the patient had. And as a function of the model rank, which is the x-axis here, you can see that the imputation error goes down as you increase model rank. But it goes down faster. This is the pink and cyan lines. It goes down faster if you use sort of tailored loss functions compared to if you use just quadratic loss functions, which is the yellow lines. Okay, so it seems like we are getting a benefit to using tailored loss functions. But I guess the other interesting phenomenon here is that you get better and better as you get to higher and higher rank. Okay, so it's, this is a low rank but not very low rank data set. Okay, this real hospitalization data set. Let me show you a pretty cool application to dealing with high-dimensional categorical variables, which from a practical data science perspective they're like the bane of practical data science, right? You get some data set from some company, and there's like, product ID, and you don't know what to do with your product ID column. Or there's store location, or there's something else like this. Okay, and the problem is, and so let me show you an example with location. Okay, so here this is an example where we're trying to predict the number of labor law violations of these various different companies. Okay, so every row is a company, and we know where they're located. We know a bunch of other things about them, 250 other things about them, but we also know how many times they violated U.S. labor law. Okay, so we're going to try to predict how many times each company will violate U.S. labor law, and this is maybe so we can target our enforcement efforts to the companies that are the worst players. Okay, but we've got a problem here, which is that probably the location is important. Here I'm encoding location using zip code, which is like mailing code in the United States. And so we think that's important, but there are a lot of them. There are 33,000 of them, and we only have 200,000 examples. Okay, so if we turned this into like a one-hot encoding, we would have too much. The data would be too wide. Okay, and we would end up overfitting. Okay, so what do we do? So here's one idea, is to take these zip codes and find some other data about zip codes. Okay, so here I'm taking, so think of this as the data table where zip code is the primary key. So I've got zip code, and I've got a bunch of other things about each zip code, so maybe the unemployment rate, the mean income in that zip code, maybe the crime rate, the quality of the schools, et cetera. Okay, so 150 columns of demographic information. And I can fit a low-rank model on this, and what I'm going to get in sort of the rows of X, right, is a vector representation of every zip code, every location. Okay, and I can think about that as an embedding of these zip codes into a demography space. Right, that's determined by these other features. Yes?
Sorry, but I mean, there's also a quite natural two-dimensional embedding of zip codes, right?
Yes, there's a geographic embedding of zip codes. So do you believe, okay, so, yes. Yes. Okay, so if you were going to use a linear model afterwards, then I would argue that the geographic encoding would be a very bad encoding, because I don't believe that there's any phenomenon like, labor law violations increase as you go north. Right, or decrease as you go east or something. Okay, maybe this involves some knowledge of U.S. geography, so it's more complicated than that. Yeah, I mean, if you're using some kind of like, deep net, then maybe, actually. So actually, we didn't try this, but yeah. Yeah, okay. If you're concerned about overfitting, then that, yeah. Okay, this is an interesting point. With a linear model, it's definitely a bad idea. With a deep net, it's not obvious. Okay. Okay, so we're going to encode these zip codes into nomography space. Here's an example. First, I'm plotting them in 2 dimensions. I'm encoding them into 2 dimensions, but later I'm going to encode them in 10 dimensions. And actually, this is kind of nice that you can put them into any dimension that you want. So here you'll see that Cupertino and Sunnyvale, which are 2 places that are both in Silicon Valley, are very close to each other, whereas someplace in Kansas, a small town in Kansas, is very far from part of New York City. So you can't tell if these are right or wrong, but let's see how well they perform. Okay, so I'll build 3 different feature sets in order to predict labor law violations. Okay, one is categorical, so I'll expand the zip code to a categorical variable using that one-hot encoding. One is concatenation, so I'm going to join these 2 tables on zip code. So in effect, I'm replacing the zip code by all of these demographic features for that zip code. And the third is replacing the zip code by the low-dimensional zip code features. Okay, and then we tried sort of fitting several different models on top here. I'm showing results for a supervised deep learning model, which was the sort of default deep learning model in H2O, which is a machine learning package. So we wanted to test the impact of the features, not of the supervised method. So yeah, the hope is that these results are robust to the learning method. So you'll see, it's not surprisingly, the runtime is much higher for this categorical encoding because it has many, many more features. What's interesting is that it actually, so the categorical encoding does achieve a lower training error compared to the concatenated one, right? So it's able to fit more precisely because it has more information. But it also overfits a little bit. So the test error is a little bit higher than the training error. But if you use these low-rank features, you actually get a lower training error and a lower test error than either. And this is kind of interesting, right? Because these low-rank features are drawn from, right, the same information is present in the concatenated features as in the low-rank features. So presumably if your neural net were really strong and powerful and amazing enough, then it would be, like, if this is the right information, right, if these low-dimensional features are the right information, it should be able to extract that information, but it doesn't. So here's a place where we actually do see a benefit to using a more structured learning method. Okay. Cool. Okay, so at this point in sort of my development as a researcher, I started thinking, like, these low-rank models are working extraordinarily well. This is weird how many domains they're working in. So I'm going to try doing them in a really, really strange domain where you would not expect them to work. And I'm going to see how well it works. Okay, so this is this really crazy application. Okay, so this is the application of low-rank automated machine learning. So here, what I'm going to try to do is when you give me a supervised learning data set, I want to predict what the best algorithm is and the best hyperparameters for that algorithm as fast as possible. Okay, so an easy way to do this would be to compute the cross-validated error of every algorithm with all possible hyperparameters, but that would take too long, right? I would have to fit many machine learning models. Okay, so instead I want to do this quickly. Okay, so this is a paradigm for trying to approach this problem. Okay, so given, let's suppose I have M data sets, right? The data set that I want to do this thing really fast on is not the first data set I've ever seen. In fact, I've seen many other supervised learning data sets in the course of my life as a machine learning researcher, so I want to allow my algorithm also to have seen such things. Okay, so M data sets and machine learning models, which you can think of as algorithms together with hyperparameters. Okay, I'm going to measure the cross-validated error of every model on every data set. Okay, remember this is like train time, so I'm allowed to take my time here as long as at test time I do things fast. Okay, I'm going to form an M by N data table. Okay, so as many rows as data sets, as many columns as models. Okay, and I'm going to fit a low-rank model to this data set. What's that going to give me? It's going to give me a low-dimensional vector for every data set, which I can think of as the latent data set features, and a low-dimensional vector for every algorithm, which I can think of sort of latent features for that algorithm. Okay, now you might ask, like, is this matrix really low rank? How well does this work? Okay, let's suppose this were true, okay? Okay, so now when a new data set comes along, now here's the part that I really care about, okay? When a new data set comes along, I would like to know how every model performs on that data set. So I could just pick the entry that had the smallest error. Okay, this is essentially what data scientists do in practice, right? You run a bunch of models, you pick the one with the smallest cross-validated error, and then you assess how it performs on your test set. I'm not including that part. Okay, but I don't know what these values are. But you can see that if I look over in this factorized view, right, the number of question marks decreases, right? If I knew the latent vector corresponding to this data set, right, then I would be able to just multiply that latent vector by this Y matrix and impute the performance of every model on my data set. Okay. Okay, so let's imagine, so how am I going to estimate that latent vector? So the way I'm going to do it is I'm going to observe the results of certain models on my data set. So maybe I'll pick 3 models to run on my data set. I'm going to use those 3 models to estimate that latent vector, just using least squares. Okay? So now I've got an estimate for my latent vector for my new data set. And now I can do imputation, right? I just multiply my latent vector times the Y matrix. That gives me imputed values for all of the models on my data set. Okay, and I can pick the one that's the smallest. Okay, and say that's the model that I suggest that you run. Okay, or maybe I can pick the 3 smallest and say, why don't you try each of these 3 models and pick the one that's the best. Okay, so does this work? Okay, so here's an initial test, right, which helps it get at this question of like, what is the rank of this data set? So let's look at, let's say if I pick, I look at the top 3, so the lowest 3 imputed cross-validated errors. Okay, and I say, what's the likelihood that one of the lowest 3 imputed errors actually correctly identifies the correct algorithm? Okay, and you can see this is increasing as I select more and more entries. And it's also increasing in the rank of the model. Okay, but so rank 5 model doesn't do super well. A rank 6 model does, rank 9 model does better. A rank 15 model does better. A rank 25 model does better, but not much better. Okay, so once again, you're seeing this phenomenon that the data isn't exactly low rank, but maybe it's approximately low rank. Okay, so even by the time you got to rank 15, you're doing very well. Okay, you're getting the right algorithm type 90% of the time. It's like pretty good. Okay, so there are 2 more parameters that I need to tell you about to describe how this method for automated machine learning works. So I guess one was the rank, right? And this plot suggests that a higher rank is better if you can afford to estimate it. Now, of course, right, to estimate a rank 15 model, you need at least 15 observations. Okay, so it's not completely free. And if you had a time budget, right, maybe you don't have time to estimate 15, right, to fit 15 machine learning models. Okay, so there's sort of a natural strategy, which is you fit 1 model, right, and then you predict. And then if you have more time, then you could fit 2 models and then predict. And if you have more time, you could fit 4 models and then predict. If you had more time, you could fit 8 models, predict. Okay, so by this doubling scheme, you can actually sort of get within a factor of 2 of the best you could do. Okay, so the other parameter is which models should I choose to observe, right? Some models are going to take a long time to run. Some models are going to, you could run very quickly. Okay, so the way that we approached this problem was using this idea from classical experiment design, which says if you have an unknown vector that you're trying to estimate, and the information you can gather on that vector consists of linear functions corrupted with Gaussian noise. Okay, so here the unknown vector is x, the latent vector for our data set. The linear functions are the columns of y. Right? And in this Gaussian noise model, it's not right, but it's a good first start. Then the variance of your estimator for x looks like the log determinant of this matrix inverse. Okay? So that's cool. So I can minimize the variance of my model by maximizing this quantity. Okay, where here the VJs, I would think of the VJs as indicators of whether I select that model to observe or not. Okay, and here what I've done is I've relaxed those VJs to continuous values, and I've added an additional constraint that encodes my time constraint, which says that the sum of the times that it takes to run each model times the indicator that I run that model should be less than or equal to my time budget. Okay, so here I'm able to encode this trade-off between the information that I get about each vector, about my latent vector by running each model, and how long it takes me to run that model. Okay. I should mention also that this objective is actually submodular, and so you can also do a sort of greedy approximation in order to decide which models to observe. Okay, so now we've got a complete specification of an algorithm, and we can run it actually against other automated machine learning algorithms. And what's kind of shocking, so here I'm going to show, so our algorithm is called OBO. That's what I just described to you. That's in red. The green line corresponds to really the same algorithm, but instead of using optimal experiment design to choose the models to run, we randomly choose from among models predicted to run in the right amount of time. And then the third is a state-of-the-art method called autoSKLearn, which is this blue line. Okay. So you can see, number one, that OBO and this random method are able to return reasonable answers much faster than autoSKLearn. AutoSKLearn takes 16 seconds to return any answer, and we're returning like sensible answers within 1 second. Okay. And then the second thing to notice is that after autoSKLearn starts returning values, performance is kind of neck and neck. Yeah, sometimes OBO is a little bit better, sometimes autoSKLearn is a little bit better, but they're approximately, they're similar. And here you might say, why do I need a machine learning model in 1 second? And I would say, well, maybe your data set, if you scale up these data sets, right, then you're talking about machine learning models in 100 seconds instead of 100,000 seconds. Okay. Okay, but you can also see the optimal experiment design. It matters a little bit. The red line is consistently below the green line. Okay. Okay, so at this point, I started feeling very suspicious. I was like, this is crazy, right? So the normal justification that people give for why data sets are low rank is they say, well, I mean, they talk about the movie lens data set, right? This is the example that people always like to give. And they say, well, maybe people's preferences for movies can be described by their preferences for genres, right? And every movie, participates, is in some small, right? There's a small number of genres, and you can say how much is every movie in every genre, right? And okay, so the interactions between these gives the ratings. Okay, and so the point, like the important thing there is that there's a small number of genres that completely explains the data. And in these data sets, I actually just don't believe that phenomenon, right? I think that people are complex. I think that machine learning data sets are complex. I think that's too simplistic a story. Okay, so let me give you a slightly more complex story and show how low rank arises even with this more complex story. So let's suppose that our data set, now I'm going to think about a real valued matrix again just for convenience. So let's suppose that it's generated by a latent variable model that's of this form. So for every row, there's going to be a latent vector alpha, okay, that could be arbitrarily high dimensional, but lies in some set script alpha. Okay? And for every column, there's a latent vector beta that lies in some set B. And my matrix entries are generated by some function of alpha and beta. Okay, so let's think of examples of this model. So here's the simplest example. Maybe the set A is the set of all k-dimensional vectors. The set B is also the set of k-dimensional vectors, and this function is just the inner product. Okay, in that case, you can say what the rank of A is. What's the rank of A? K. Great. The rank is K. Good. Okay. So what about this model? Okay, so let's say alpha is univariate, so it's between 0 and 1. Beta is also univariate. It's a number between 0 and 1. And I've got some function of alpha and beta. And I'm not going to tell you anything about the function yet. So what's the rank? Are there bounds on the rank of this data set A? Okay, we're getting near time, so I'm going to say no. Generally, it's full rank. Okay, you can make the function g as wiggly as you want. You can make this full rank. Okay, so we might consider sort of smoother notions of this. So let's consider the rank of an entry-wise epsilon approximation to A. Okay, so I want to find a matrix X that's within epsilon of every corresponding entry of A, right? But whose rank is minimal. Okay, right. So you could call this like the epsilon rank of A. And you can ask our latent variables approximately low rank in this sense. And the answer is yes. So let's talk about univariate latent variable models first. So univariate ones. So here's the key assumption. So we've got the same modeling assumptions we had before. So alpha and beta are univariate between 0 and 1. A is g of alpha and beta. And I'm going to add this assumption that g is analytic okay, with a bounded norm of any derivative. Okay, so in that case, I can show the rank of an entrywise epsilon approximation to A grows as log of 1 over epsilon. Okay, so this is very slow. And it means that this matrix is very well approximated by a low-rank matrix. Okay, it's not exactly low, yeah?
So this means that there is a representation which is low rank. So you say that you don't believe in the existence of
I don't believe in the story.
Sure, but you just built a story. Say the same thing.
No, so my story is something different, right? My story is, sorry, yes. These are low dimensional, right? The alpha and betas are low dimensional, yes. I'm gonna get to the story that I believe a little better on the next page. Okay, yeah, these alpha and betas I still don't believe. Univariate is too strong, yeah. Okay, but the proof technique is very similar, so I want to show you the proof for the univariate case first. Okay, so here's the idea. It's extraordinarily simple. So I'm going to take G. I'm going to expand for any alpha. I'm going to expand around beta using a Taylor series expansion. So I get this term that depends on the first derivative of G evaluated at alpha times beta, second derivative of G evaluated at alpha times beta squared, etc. Now I can write how many terms do I need to approximate this decently well. So if I want to approximate it with an epsilon, I need log 1 over epsilon terms. Okay, and that's just by calculus. Okay, now I'm going to collect these things. So I see I've got a thing depending on alpha times a thing depending on beta, right? Thing depending on alpha times thing depending on beta. So I can collect these into one vector that depends on alpha but not beta, another vector that depends on beta but not alpha. And at that point, I have a rank decomposition. Okay, now is it a low rank decomposition? The answer is yes, because the number of terms I needed was like log 1 over epsilon. Okay, so that's the proof. It's super straightforward. Okay, but now let's address a higher dimensional case, and things get more complicated when the latent variables are higher dimensional. Okay, so here is a collection of assumptions for which I can prove something nice. I don't think these are the right ones. I think that you can do something stronger. But let's say that the sets alpha and beta have bounded support, and let's say that G is piecewise analytic, and on each piece, the derivatives of G grow no faster than exponentially in the order of the derivative. Okay, so I would say, like these are weak assumptions if you believe that analyticity is weak, and if you believe analyticity is strong, then they're strong. The order of the derivative thing is not too much of a problem. So polynomials in alpha and beta, or even exponentials of polynomials, obey this. Okay, so in this case, so now we're in a setting, right? Once again, right? These guys have bounded support, but they could be high dimensional, arbitrarily high dimensional. Okay. So then how does the rank of an epsilon approximation to A? In this case, we're not going to be able to get results that don't depend on the dimension of your data set. Okay, so we're going to get dimension-dependent bounds. How does the rank of an epsilon approximation change with the number of rows and columns? Okay. Do you have any guesses? Right, so of course the rank is always bounded by the min of M and N. Okay, so I wouldn't be telling you about this unless I had something that was better than min of M and N.
Half of the min?
Half of the min, okay. Any other guesses? Okay, so we can do as well as log. Okay, so the rank of these nice latent variable models grows as log of the sum of the dimensions. But the factor we have to pay in exchange is over epsilon squared. Okay, so we can't do very good approximations anymore, right? If the latent variables are truly high dimensional, you can't do sort of very precise approximations. But if you're willing to settle for a approximation within 0.1, if your data set is very large, then it does look quite low rank. And this is kind of the phenomenon that you see in something like movie lens, say.
Yeah, so you go back to square one, you have a model.
Yes.
Leads to a low rank matrix.
Yes.
You say you didn't.
Yeah, so it's a more general class of model, right? I don't think that you would look at this and say, oh, you're baking in the low rank.
Low rank or not low rank.
Yes.
So as soon as you're low rank, there exists a representation.
Yes.
However,
Exactly. Yeah. So I mean, this is not a, I mean, the best theory also, you're right, it provides a guide to practice, and this is providing what I consider more a better explanation, but it's not a guide to practice. Yeah. Okay. So the proof for this is actually super straightforward. There's only one more ingredient compared to the ingredient in the univariate case. So here we do the Taylor expansion as before. We collect the arguments as before, the ones depending on alpha and on beta. But now these things are actually quite high dimensional because I have to sort of vectorize the gradient depends on the dimension. The Hessian depends on the dimension squared of these latent vectors. Okay, so these things end up being very high dimensional, even if the number of terms is small. Okay, so now what I do is I use a Johnson-Lindenstrauss lemma to reduce the dimension while preserving the inner product. Okay, and the Johnson-Lindenstrauss is what gives the epsilon squared, and it also gives the log. Okay. Right, we use some variant that controls the inner product. Not important. Okay, so I think we're at time. So what did I show you? I showed you some applications, some examples that show big data is low rank in social science, in medicine, and even in machine learning. Just kind of weird. And I showed some explanation for why this should be true, maybe. If you believe that my model is more general than the typical genres, not too many genres model. And I showed how to exploit low rank in order to fill in missing data, reduce the dimensionality of feature vectors, and more generally turn big, messy data into small, clean data by using these low dimensional representations. Thanks.